Of all the world's drinking water, 1/5 is stored in one place, the Great Lakes. They're so big, they're like inland seas. So vast, they make their own weather. Without them, a large part of North America would be arid. They're filled with enough water to flood the continental United States 9 feet deep. But water levels are changing dramatically. To understand where the waters are going, you have to know where they came from and unlock the mysteries behind the Great Lakes. The Great Lakes deserve their name. They cover an area bigger than Utah and hold 5,500 cubic miles of fresh, drinkable water. The deepest of the 5 lakes, Lake Superior, is over 1,300 feet deep. Lake Michigan and Huron provide drinking water for over 10 million people in Chicago and Detroit. Between Lake Erie and Ontario is the mighty Niagara Falls. At its peak, over 40 million gallons flow over the falls every minute. It provides electricity to roughly 5 million homes. The Great Lakes are unique. But how did these 5 vast lakes form? What force was so powerful it reshaped solid rock and carved such deep depressions? Beneath a sea of water and silt, the lakes cover up the evidence of their origins. Yet on an island in Lake Erie, one clue is exposed. Kelly's Island sits on ancient rock. The rock is scarred by strange grooves, some more than 15 feet deep and 400 feet long. If we were to peer into the depths of the lakes, down to the bedrock, this is what we would see. Dr. Jeff Dick from Ohio University is looking for clues to how the lakes formed.
The groove that we're sitting in here provides a very interesting tidbit of information as to how the Great Lakes formed. The area that we're in, this groove, was obviously gouged out by some force.
But which force carved these lakes? One of the Earth's most dramatic sculptors is volcanism. Boiling hot magma erupts from deep within the Earth. As it cools and hardens, it can produce incredibly strange geological formations. Did volcanism do it? The rocks at Kelly's Island hold the answer. Tiny coral fossils. When rock melts, the fossil record is usually destroyed. If lava had formed the grooves, these fossils would probably have been erased. The next suspect is water. If water carved the Grand Canyon, why not the Great Lakes? But water has an alibi: fractures in the rock.
If it had been formed by running water, a stream, a river, it's more than likely that that stream or river would have taken advantage of this weakness in the rock and actually followed it, meaning that the fractures would direct where the stream flows. And in this particular case, the grooves are running almost perpendicular to them, suggesting that maybe there's another force at action here.
So if volcanism and running water didn't shape the grooves, what did? There's another suspect: ice. But how does mere ice carve stone? Where better to find out than Earth's most spectacular frozen landscape, Iceland. This is the Vatnajokull glacier. It's the largest sheet of ice in Europe. It covers 3,200 square miles. That's more than twice the area of Rhode Island. In places, it's over 3,500 feet thick. Geologist Andy Russell knows it like his backyard.
This glacier, although it may look as if it's sort of sitting there and, fairly passively, the actual ice is always moving forward, even though the edge of the glacier may be stationary.
This time-lapse footage shows the glacier's movement speeded up hundreds of times. Behind the leading edge, the ice moves up to 3 feet per day with a heavy step. A glacier a mile thick exerts about 2,000 pounds of pressure per square inch. That's the weight of 115 cars on 1 square foot of land. For all its bulk, ice isn't as tough as it looks. To cut into solid rock and form the basins of the Great Lakes, ice needs another ingredient. Andy Russell demonstrates.
I shall take a bit of ice, which has a smooth surface, and we'll drag it across this tin foil. Really, there's very little damage to the tin foil. So we'll now move on to the dirty ice.
Dirty ice is embedded with small rocks and stones.
We can see it's got all this grit on it, and we're going to see what it does to the tin foil. The tin foil's been shredded.
That's how a glacier does damage. As it travels, the glacier picks up stones and rocks. The weight of the ice holds them against bedrock. Then the moving mass scours the land like a huge sheet of sandpaper. When the glacier finally melts, it leaves behind a vast depression filled with glacial meltwater. Normally, it's impossible to see glacial erosion in action. The process is hidden beneath a blanket of solid ice. But here in Iceland, the base of the glacier is exposed. It shows Russell just how ice grinds through solid rock and explains how ice could carve the Great Lakes.
We've got layers of ice, which you can see in here, mixed with layers of debris, or it's dirt, here and also here, and obviously this big bit of rock here, this boulder. The boulder tells us several things. All these little scratches crisscrossing, and the fact that this surface here is extremely flat tells me that that boulder's actually been at the glacier bed. It's been held in the ice, and then it's been ground against the bedrock.
This glacier is melting, and as it melts, it drops its load. Iceland is littered with thousands of dropped rocks. It's this action of rock grinding against bedrock that may have gouged out the strange grooves on Kelly's Island. But where's the proof that a giant glacier passed over the Great Lakes area? Here, near the shores of Lake Ontario. Scientists call this an erratic boulder, meaning it doesn't belong here. This giant boulder is made from granite, a type of rock not found within 100 miles of this area. Like the boulders in Iceland, it was trapped inside ice for thousands of years, dragged across the bedrock, and then dropped in its new home. The glacier that moved the boulder must have been enormous. The proof again lies in the rock of Kelly's Island. From the chemical makeup of microscopic fossil shells, scientists can tell the water was once much colder. Tiny clues lead to a vast conclusion. A glacier up to 2 miles thick covered most of Canada and a large part of the US. It was called the Laurentide ice sheet. For over 1 million years, the enormous glacier advanced and retreated over the land, back and forth. As it did, it gouged out the 5 enormous lake basins. The ice sheet passed over the Great Lakes. But how long did it take for ice to carve through solid rock and form the basins of the Great Lakes? Geologists think that the Laurentide ice sheet moved across North America for over 1 million years. But how long did it take to gouge out the 5 vast lake basins? In Iceland, the Vatnajokull glacier erodes bedrock just as the Laurentide once did in the Great Lakes. Andy Russell measures the ground-up rock washed away as sediment.
This equipment measures the cloudiness of the meltwater. The cloudiness of the water gives us a sediment transport rate in the river. And if we average that and scale it up over longer time spans, we can figure out how rapidly the catchment is eroding.
Measure the sediment produced, average it up over time, and this glacier grinds away around 1 foot of solid rock every 100 years. But did the Laurentide erode rock at the same rate? It was, after all, over 1,000 times bigger than the Vatnajokull glacier. John Menzies has come to Mohawk Bay on the shores of Lake Erie to find out. The answer lies hidden in these cliffs. They look like mud, but they're ancient rock sediment. This was once solid bedrock. It was crushed by the Laurentide ice sheet and deposited here.
Based on the evidence that we're trying to sample here today, we hope that this will illustrate how the Great Lakes basins were formed and developed.
These tiny rock particles hold a secret. Menzies sets the sample in resin and slices it into thin sections. Normally, glacial erosion produces rock grains with jagged edges. These grains are nearly round.
If you look at this particular thin section, you can see this particular piece of rock, and you can see around it the effects of rotation, kind of indicative of the sediment being moved underneath the ice sheet and rolling and rotating beneath the ice. So in other words, the sediment has been tumbled and moved and rotated and sheared time and time again.
But how can a glacier produce both jagged and smooth rock grains? The explanation? Some of the ice inside the Laurentide glacier moves faster than other areas of ice. The fast-moving ice is called an ice stream. Ice streams are like rivers of supercooled water. Water that's well below freezing, but doesn't solidify. These rivers can flow up to 3,000 feet a year, 10 times faster than the surrounding slow solid ice. Working 10 times faster, they can potentially dig 10 times deeper. More proof that the Laurentide contained fast ice lies beside Lake Ontario. This is an aerial photograph of the shoreline. It shows strange, elongated hills. These are lumps of sediment called drumlins. As the glacier retreated, they were left behind. Here's how they formed.
So if we produce a blob of toothpaste, And this we take as the base of the ice. And so as the ice deforms, so does the toothpaste deform, and we produce this nice linear. You can actually see the small lineations, drumlin-like, streamlined forms that are actually being produced simply by moving one interface over another interface.
Just as fast ice leaves a trail of long, thin drumlins, it also tends to carve out long, thin lake basins. If fast ice alone carved the Great Lakes, it could have taken as little as 100,000 years. The ancient ice sheet gouged out millions of tons of rock, ground it into fine sediment, carried it away by meltwater, and flushed it out into the Atlantic Ocean, left behind 5 enormous basins. The deepest, Lake Superior, more than 1,300 feet. The Great Lakes. But when did the enormous Laurentide glacier melt and the basins fill with life-giving fresh water? Francine McCarthy holds a clue, a 12-foot tube of mud called a sediment core. The sample was taken from the bottom of Willoughby Bog, a swamp between Lakes Erie and Ontario.
This keeps a very good record of what went on when people weren't here to keep the history.
The core is made up of mud, pollen grains, and sediment deposited in the water when the lakes formed.
We remove material for radiocarbon dating, and the dates are about 1,700 years ago here, about 7,500 years ago here, and about 9,000 years ago near the base.
The cores reveal water was present at least 9,000 years ago. But beneath the 9,000-year-old layer is one even older. It's the last layer before hitting bedrock, so it must be the first layer deposited in the water. If McCarthy can date it, she can pinpoint when fresh water arrived and reveal the age of the lakes. But to date the layer, she needs organic material.
You can see the color contrast between the very inorganic and the bog material. This is impossible to date using radiocarbon dating, conventional radiocarbon dating techniques, because you can see that there's very little organic material here.
Just rock and clay, a dead end. But why are the early lakes lifeless? To find out what the early Great Lakes looked like, we need to return to Iceland and the Vatnajokull glacier. Here at the base of the glacier is a newly born lake. Its basin was carved by ice and filled with meltwater. This is how the Great Lakes looked tens of thousands of years ago. And like the early lakes, this place is dead.
There was virtually no life in these proglacial lakes. It's very cold, it's a very harsh environment, there's very little light, so your whole ecosystem is unable to really get kick-started.
The reason? The water's strange milky color. These lakes are loaded with ground-up bedrock, sediment washed down from the glacier. This sediment blocks out light, and without light, small organisms like algae can't survive. No plants, no food, no life. As the Vatnajokull glacier continues to melt, more water will flood this lake and dilute the sediment. Eventually, it will settle on the bottom, just as it did over thousands of years ago in the Great Lakes. This is the pale gray layer McCarthy discovered. The mystery remains. Scientists have to find some other way to date the age of the lakes. The answer could lie hidden in one of North America's most spectacular geological formations, Niagara Falls. Niagara is the mightiest waterfall in North America and one of the Great Lakes' most awesome features. On average, 150,000 gallons pour over every minute, enough to fill over 60 Olympic-sized swimming pools. Niagara holds the answer to a prehistoric mystery. When did the ice retreat and the Great Lakes fill with water? John Menzies has come to investigate. It's the first time he's gotten this close to the falls.
It's just utterly incredible. You see the volume of water that's coming over per second. All the water from the central part of North America is flowing right over here as we stand. Fantastic.
It's possible to date the arrival of the water in the lakes because Niagara behaves very strangely. The falls are moving. Every year, they take one step back, 12 full inches toward Lake Erie. The reason for this movement is the rock. The falls are built on 2 layers of rock. At the top of the falls is a hard layer of limestone, known as cap rock. Underneath is a softer layer.
This is a piece of Queenston shale, which is the weaker rock from underneath the cap rock for this area of regional geology. And in fact, it's very, very easily to break, as you can see. Bingo.
The weak shale at the base of the falls is relentlessly pounded at up to 70 miles per hour. The constant hammering erodes the shale below and undermines the cap rock above.
The cap rock gets left like a cantilever effect, and then it simply breaks off, and it breaks off every so often, fairly dramatically. In fact, if we look at the falls, there's a huge rock that's actually fallen off in the last 100 years. In a sense, you can look at Niagara Falls as being, if you like, an ongoing process of destruction. Perpetual destruction, perpetual change.
The destruction means that the falls act like a giant timepiece, an enormous clock that allows geologists to date the age of Niagara and the lakes themselves. Until 100 years ago, the falls eroded 3 to 4 feet a year. As water was diverted for hydroelectric power, the erosion rate has fallen, but the falls are still eroding roughly ½ an inch a month.
Eventually, given time, the hotels, the casinos and so forth are going to be left behind in the track of the falls as the falls retreats to the south and leaves this touristic area in isolation.
If the falls continue to erode at this rate, in about 50,000 years, the falls will reach the base of Lake Erie itself. As the falls retreat, they carve a giant canyon, the Niagara Gorge. 3 miles downstream from Niagara, geologist Francine McCarthy can date the Great Lakes by searching for the fall's birthplace. The secret is hidden not in rocks, but in clamshells.
Well, that's perfect. We can identify that to species. It's definitely the kind of thing we want to radiocarbon date back at the lab.
This species of mollusk lives in Lake Erie. It was carried downriver and over the falls. The surging water wedged the mollusk into cracks at the base, where it died. The falls moved on. The shell remained. By carbon dating shells like this, McCarthy can prove Niagara Falls roared over this exact spot 7,000 years ago.
The water level would have had to have covered this area in order to deposit the little aquatic clams in the crannies where we find them.
Further proof can be seen in the strange rocks scattered around this whole area. These holes were cut into the rock by the constant pounding of water over the falls. But this isn't Niagara's birthplace. The further McCarthy walks from the falls, the further back in time she travels, and the older the shells she discovers. By analyzing shells found all along the gorge, McCarthy reveals the life cycle of the lakes. From Niagara's spectacular location today to their location in 1678, when the first written account was made. Downstream to the Whirlpool Rapids, 5,500 years ago. Through Niagara Glen, where McCarthy's shells reveal their location 7,000 years ago. To Queenston, 10,500 years ago. And finally, 7 miles downriver from the falls, where a natural ridge called the Niagara Escarpment cuts across the land. Scientists discover the oldest shells yet.
The Niagara Falls are 12,600 years old. They've been operating since water started melting from the Laurentide ice sheet.
And if Niagara Falls is 12,600 years old, then the Laurentide glacier must have retreated at least 12,600 years ago, exposing the 2 lower lakes, Erie and Michigan. The mystery is solved. Like Niagara, the Great Lakes have continued to evolve over the millennia. But some changes happened much more dramatically than anyone imagined. Today, rainfall on Lake Superior takes 204 years to travel through all the other lakes before it reaches the Atlantic Ocean, more than 2,000 miles away. The Great Lakes flow east, and always have, or so geologists thought. Scientists studying fossils in the Gulf of Mexico uncover surprising species. It forces them to reevaluate what they thought about the Great Lakes. Scientists analyzing 14,000-year-old shells discover the water in the Gulf of Mexico must have been less salty than today. But why? Only one source of fresh water was vast enough to dilute the Gulf: the Laurentide Glacier. Fossil records suggest the meltwater drained south along the Mississippi River to the Gulf. But then, nearly 13,000 years ago, some titanic force diverted the flow from south to east. The question is, what force was powerful enough to divert the Great Lakes? 13,000 years ago, some unknown force diverted the flow of meltwater from the Laurentide Glacier. Geologist Alan West searches for answers on the shore of Lake Michigan.
This is a visual line that's actually where our greatest interest lies. The Great Lakes really began right at this line in the sediment.
West finds tiny specks the size of sesame seeds. They're made of carbon. West believes they're all that remains of a vast forest, incinerated at sizzling temperatures. But the most important clue lies inside each grain, a dazzling secret.
These small black dots, they're almost pure carbon, and when we check them with an electron microscope, we find that they contain millions and millions of diamonds.
Each diamond is 1,000 times smaller than a pinhead. They're known as impact diamonds. They form under intense pressure. But what created them? Something big hit this area at great speed. It packed a huge punch. Alan dumps a sample over a magnet. Incredibly, it contains metal.
Definitely magnetic grains in there. You can see them coming out.
The magnetic grains are iridium. Iridium is extremely rare on Earth, but common in rocks from space. West's theory is 12,900 years ago, a massive comet strikes Earth and showers the region with iridium. wildfires sweep across the area and destroy all vegetation. The shock wave breaks up part of the Laurentide glacier. Billions of gallons of water are released.
It's well known that when these meltwater outburst floods occurred, they're very, very abrasive. They can change the shape of valleys, they can scour bedrock, so it's entirely possible that they dug the Great Lakes deeper or at least removed sediments that were already there.
Thousands of tons of rock, soil, and debris are flushed south. Like a giant plug, it blocks the Mississippi. The water backs up. Lake Ontario swells and bursts its low eastern bank, and the St. Lawrence Channel opens up.
All the evidence shows that the Gulf of St. Lawrence opened up and water went to the east, but stopped going to the south.
West believes it all happened in just a few months. Since then, the lakes have drained east into the Atlantic Ocean. The new direction allowed small settlements to become the great cities of Montreal and Quebec. Rarely does the course of history change so suddenly and so dramatically. Yet the evidence is circumstantial. If a comet hit, where's the crater? In 1999, on the bottom of Lake Ontario, geologists discovered a crater half a mile wide. It's still undated. West believes it might be a fragment of the comet that diverted the water. No other craters have been found, but West isn't surprised. The comet could have done its damage and simply melted away, because comets are mostly ice.
This is the perfect crime, the ice bullet. You shoot someone with an ice bullet, and you can't tell who did it. Earth got hit by an ice bullet, actually thousands of them, and so the evidence is minimal.
As the last ice age ends, all 5 Great Lake basins are slowly revealed and filled with fresh water. But there's one huge difference between these early lakes and the ones we see today. They aren't linked. To unite them will take a force of nature more powerful than a comet. Today, the Great Lakes are connected via a network of rivers and channels, a 2,000-mile water system. This wasn't always the case. The upper lakes, Superior, Michigan, and Huron, weren't always connected to the 2 lower lakes, Erie and Ontario. Francine McCarthy is trying to find out how they joined.
We've taken some samples all along the shoreline of Lake Ontario and Lake Erie, and we're going to look under a microscope at small seeds and pollen to find out the age of the samples and what kind of environment they were deposited in.
5 miles inland from Lake Erie, McCarthy discovers a tiny clue: wild rice. This is incredibly strange. Wild rice doesn't grow inland.
Wild rice needs to have sort of agitated, well-oxygenated water in order to be happy. The fact that there was a lot of wild rice indicates that the water level in Lake Erie was higher than it is today.
Lake Erie must have been much bigger and more turbulent.
The wild rice date of 4,230 years tells us that water levels rose quickly, instantaneously, in both the Erie and Ontario basins.
But why? McCarthy has a theory. Over 4,200 years ago, Lake Huron swelled and burst its southern bank. A torrent of water pushed south. Lake Erie suddenly expanded, and wild rice took root in its disturbed waters. the St. Clair River opened and the lakes joined.
That's when we begin to see the truly modern conditions. Since 4,200 years ago, there's never been any other way for water to flow out of the upper lakes but through the St. Clair River into Lake Erie, over the falls, and into Lake Ontario.
But why did Huron swell and flood south? The mystery deepened when scientists noticed something strange happening in the Great Lakes. In each lake, the water level in the north is falling, but in the south, it's rising. What mysterious force is behind these strange phenomena? Professor Doug Hunter and divers Luke Clyburn and Kathy Trax are plunging into the lake's past to find evidence of ancient water levels. They start their investigation in Lake Huron's southwest corner, in the harbor town of Lexington. They need evidence to show whether this imbalance in water level is a recent phenomenon or if it's been going on for millennia.
Today, we're going to put divers in the water, and as we dive down, we're looking to see if we can find something that will show this is where the lake levels were some thousands of years ago.
Lake Huron is over 700 feet deep in places. But the area the team are interested in is only 40 feet deep.
Right now, we're about 2.5 miles east of Lexington Harbor. Underneath us, in 40 feet of water, is an area where we suspect there may be some interesting finds that would give us some insight into the Great Lakes history.
This section of the lake bed has never been surveyed. The team scour every inch for evidence of past water levels. They're looking for something out of place, some clue to this strange mystery. "40 minutes into the dive, the team finds several large pieces of wood. From this wood alone, they can't tell if trees once grew here, or if it's just debris thrown from a boat. They need evidence like this. A tree trunk. It's still rooted in the lake bed. These stumps have never been seen before. This proves that trees once grew in this exact spot. A true discovery.
There's wood.
Boy, that was a great dive. You could see whole trees falling over, and they just went out into the sand and down.
But once we found the tree stumps, and you could see the roots of the tree stumps running down, it had to be shoreline.
This part of Lake Huron was once a forest of cedar and pine. Today, you have to dive 40 feet to reach the trees. But once you could have walked here and not even gotten your feet wet. When could you have strolled through the trees? These stumps have to be carbon dated, but samples from other locations in the lake have already told their age.
We discovered that the most recent one was 6,400 years before present. The oldest one was about 7,900 years before present. So it's quite a long range, quite a large range of dates.
6,500 years ago, Lake Huron was a fraction of the size it is today. A forest flourished on its southern end. 1,500 years later, water crept south. The southern end was swamped and the forest drowned. The St. Clair River opened, and Lake Huron joined to Lake Erie. The overflow thundered along the Niagara River and tumbled over the falls. And all 5 lakes joined. But what caused this dramatic transformation? And is it still taking place today? Mike Kramer from the Geologic Survey of Canada is investigating a strange anomaly: why water levels in the Great Lakes are dropping in the north and rising in the south. Kramer works on a remote spit of land next to Lake Ontario. It's not the water level he's monitoring. What looks like a garden shed actually holds state-of-the-art GPS technology.
We're using a GPS receiver to monitor the motion of the structure every 30 seconds. The antenna is bolted down to the floor and runs up through the roof. It's very stable.
In other words, Kramer is studying whether the shed is rising or falling. This GPS receiver picks up signals from satellites orbiting the Earth. The equipment is so sensitive, it can detect movement down to the millimeter. As a result, Kramer can determine the exact elevation of the shed, and thus the land it sits on. His findings are astounding. The Great Lakes region is rising 1 inch per decade in the north and sinking nearly 1 inch per decade in the south. This part of North America is tilting, and the pivot point runs straight through the Great Lakes. The tilt is imperceptible to us, but it affects the lake's water level.
We have a bowl of water representing a lake, this end being the north, this end being the south. And if we can imagine, as the land tilts, the water levels are rising in the south and falling in the north. It appears as though the water level is falling, and actually it's the land that's rising.
The changing land levels are tiny, but over time, all those inches add up. Ultimately, tilting is what drowned a forest. But what force is powerful enough to tilt a major part of the North American continent? Scientists think it's the opposite of the force that compressed it. Earth's surface can actually be squashed if the weight is heavy enough. Few forces are capable of compressing the crust. One is ice. The Laurentide glacier weighed around 10 million billion tons. Once it reached a certain thickness, the glacier depressed the crust 1 foot for every 3 feet of ice. It left a dent up to a half a mile deep.
About 20,000 years ago, the ice had covered most of Canada, and the great weight of that ice had depressed the crust substantially. And as the ice retreated and melted, the land underneath it then began to rebound.
Rebound began as the ice melted tens of thousands of years ago and continues to this day, about 1/10 of an inch per year. The ice sheet was much thicker in the north than it was in the south. At its thickest, it compressed the Earth the most. So when the weight was removed, the Earth rebounded more in the north. This imbalance causes much of North America to tilt. Combined with a warming climate and less rainfall, rebound is changing the outline of the Great Lakes. If water levels continue to drop in the north, vital transport routes will shrink. Industry, hydroelectric power stations, and millions of people could be affected. Eventually, the crust will rebound to roughly the position it was before the Laurentide glacier advanced over it, and the water will find its level. But until it does, the future of the Great Lakes will be as dynamic as their past.